In the last lecture I introduced the concept of propagation delay. Any hardware has a delay. So when we draw a block diagram of a circuit diagram or a circuit diagram, you give inputs and you define outputs, you sort of assume that the outputs are available as soon as inputs are given. But however fast the hardware is, the gates and other things we have inside the circuit, there has to be a finite time delay for the transmission of signals. This time is defined as, this time is called the propagation delay, and of course depends on the length of the signal path. As soon as the signals are given, the gates start switching. Basically it's a switching activity, no, from one level to the next level. Sometimes the switching is not there, sometimes they are switching based on the input conditions. Based on the input conditions and the function of the gate, you have a switching activity. So the switching activity is going to take a finite amount of time, and this propagates through the circuit. So the total propagation delay of any circuit or subsystem or even a big system depends on the length of the path that the signals have to travel from the input to the output. So when you want to design fast circuits or fast systems, naturally you have to, because one is the technology solution. What we have today is much superior to what we had about 30 years ago, 20 years ago, 10 years ago, even 5 years ago. So speeds are improving because of technology. That is one aspect. But the other aspect is, can we reduce the path of transmission? The path that the signals have to travel from input to output, if you can reduce that path, you can reduce the propagation delay or increase the speed of operation of the circuit. This is a concept which people use all the time. For a given technology, you want to maximize the speed or you want to improve the speed, then you have to go for this type of options, reducing the propagation delay by cutting the path length. But then a given job has to be done. Take the case of the full adder, a multi-bit full adder. Each full adder, the carry has to go from one stage to the next stage, stage to stage the carry has to travel. The carry circuit, we saw the carry circuit yesterday, we have a two-level gate structure, inputs AND gate, input AND gates feeding to an OR gate, output of the OR gate is the carry for that particular bit. This input is required in the next stage before the next stage can start switching. So naturally as you go on increasing the number of bits, the propagation delay from bit to bit is going to increase, and finally the time at which the reliable results are available at the output will depend on the number of stages and the delay of each stage. Now if you do not have to depend on this transmission of the carry, if you can sort of project the carry output of each stage or predict the carry of each stage, we can reduce the propagation delay. There are several techniques. Fast carry propagation is one of the standard problems in arithmetic circuit design, and you know that the speeds of computers today are very high. We talk of gigahertz computers. Gigahertz means 10 power 9. So we are talking about such speeds. Naturally people have thought about this problem and have solved this problem. So we are, as I said, this is the first level course in digital design. That is not my intention to go to all those design techniques to improve the speed of performance, all the various techniques. But conceptually you should know, it is always you can always decrease the speed, decrease the delay or increase the speed by having fewer stages. How can I have a fewer level of 2 levels of gate I set for each carry bit, and depending on the number of stages there have to be that many 2 levels. That means there are 8-bit addition, each bit requires 2 level carry circuit, so 8 into 16 levels of transmission gates. If you can reduce that level, there are 2 ways of doing it. I can predict it and see whether without having to wait for the previous carry can I start my addition of the next stage. Of course, which case you will have to always wonder what is going to happen when the real carry comes, how are you going to take care of that. As I said, these are all very many techniques we are not going to look into, but what I can do is to sort of given A's and B's, the bits to be added, bits of number A and bits of number B, some sort of a we can sort of predict or look ahead what would be the carry for each stage, and then feed those carries directly into those respective stages. In other words, do a carry computation instead of having to wait for the carry to propagate, do a carry computation and feed them all at the same time into the respective stage, which means there has to be an additional logic. That means I need to have extra hardware given A's and B's. If I want to calculate the carries of all these different stages ahead of time, I need to have extra hardware, extra logic to accomplish this. So it clearly means that at the cost of extra logic or extra hardware, I can speed up the operation of a circuit. This is something which is conceptually not very difficult to understand intuitively. More hardware, faster you can do things. If you want to do something with a single thing, single unit of hardware, it takes certain amount of time. If you have many pieces of that hardware, you can do it faster. Of course, not always. The problem could be partitioned like that, but most applications. In other words, anything you want improvement in performance has to come in at the cost of something else, and usually that something else is the extra logic. Extra logic means extra cost means extra power. So it is all trade off. At what speed do you want, and what is the price you are willing to pay. You want to pay more money, get more gates and dissipate more power. If you don't mind dissipating more power, I can possibly get a better speed up. This is the concept I want to bring in rather than the actual techniques. There are so many techniques. As an illustration of this concept, we will only look at one of the techniques. It is called carry look ahead adder. So we will talk about carry look ahead adder for speed improvement of adder, multi-bit adder. Also some people call it CLA, carry look ahead adder. As I said, can you look ahead? The carry of differences can be looked ahead as soon as the bits are known. As soon as the bits are known, can you sort of ahead of time can you do a computation of the carry and then use it when it is required, sort of a prediction by computation in advance by using extra logic. That is why I said extra logic can give you extra speed, and this technique is called carry look ahead because of that reason. So we are going to have an extra hardware which is going to generate the carry for different stages, keep it ready, and when it is required it will be used. I will give you a simple example now. We have, let us use the 4-bit adders again, A and B, A3, A2, A1, A0, and B, B3, B2, B1, B0. These are the 2 bits you want to add to get the sum S0, S1, S2, S3, and C3 would be the 5th bit that we need. When you add 2 4 bits, you need to have a 5th bit. That 5th bit comes from this C3. Now, if you look at the truth table, what are the conditions of the input for which there is a carry output? Carry output, if you remember, if you want to quickly do this, I will only do CO. There is a carry for this, there is a carry for these 3. Now if you look at these two, these are the 4 rows or 4 conditions of input for which you have an output carry. You look at these 2 conditions, these arrows I have marked here, these 2 conditions have one thing in common. Okay, 0 1 1, right. Now we will put it this way. I put the carry differently. I will remove the arrow. The last 2 rows I will put under one category, and these 2 rows I will put under another category. When both A and B are 1, we have a carry. When both A and B are 1, it is a carry, irrespective of whether Ci is 1 or 0. So there is one condition under which you have a carry. So see, we are going to design a logic to predict or look ahead. You have to design a logic to look ahead. That means I should understand the carry mechanism. I should understand the carry generation mechanism of the adder if I want to really design a circuit which can generate my carry in advance ahead of time. That is why I am looking at it this way. So carry will be generated whenever there is both A and B are 1, irrespective of whether C is 1 or 0. The other condition on which carry comes is when A or B is 1, one of them exclusive OR condition, provided Ci also happens to be 1. So that means I can now sum up the carry mechanism of a full adder as, if both A and B are 1, I get carry, that means A and B, if both are 1, the output is carry is 1, or when A exclusive or B is true, but only when A exclusive or B true, only when Ci is 1. So A exclusive or B and Ci is one condition at which carry is 1, output carry is 1. A and B is 1 is another condition for which output carry is 1. So there are 2 conditions. Look at A and B, and moment they are 1, you put a carry condition, or look at A exclusive or B and see if it is 1, see if Ci is 1, if it is 1, make it 1, if it is 0, it is not. So this is called carry generate. Carry is generated in that stage, whatever is the stage, we have multi-stage addition, 4-bit addition in this case, it could be 8-bit, it could be 16 bits, it could be 32 bits. At each stage or each bit, the carry will be generated if the corresponding bits are both 1. That is why it is called carry generate, irrespective of the fact whether the previous carry was 1 or 0. So carry is, fresh carry is generated at that stage if both A and B happen to be 1 in that stage. You do not have to look at what was the carry pushed from the previous. The other condition is when A exclusive or B of that stage is 1, the carry will be generated only when the previous carry was pushed into that. So this one I will call carry propagate. Ci is propagated from previous stage to next stage if A exclusive or B is 1. Do you understand this concept? Propagation, a carry from a previous stage is propagated or transmitted to the next stage if A exclusive or B is 1. And if A and B is 1, a fresh carry is generated and transmitted to the next stage. So output carry will depend on whether A and B is 1 or A exclusive or B is 1, but input carry is also 1. Under these 2 conditions, I have now exhausted all the possibilities of a carry generation mechanism of a 1 bit. This bit could be the 8th bit, 7th bit, 18th bit, 37th bit. I need to know what is the previous bit and the current value of A and B, then I know whether the next bit is going to be 1 or a 0 for carry. That clear? So that means I can write it as, I will call this as G, this as P. G for generate carry, P for propagate carry. Carry generation and carry propagation So I will have C as output carry as generate condition, which is A and B condition. This is going to call G, I am going to call this G, and I am going to call this term P. The propagate condition is A exclusive or B and Ci. So output carry will be G or PCI, where G stands for A and B, G stands for G stands for A and B, and P stands for A exclusive or B. Is it clear? Now let us look at our 4-bit adder. This is my C minus 1, this is my A0 B0, C0 is output carry feeding as input carry for this, C in A1 B1, output of this is called C1 feeding as input into this, A2 B2, C2 will be the output of this feeding as input to this, A3 B3. This circuit I drew yesterday also in the last lecture too. So this is A3 B3 and the output is C3. I am only interested in C3 finally. I am interested in S3, S2, S1 and S0. This is the sum and C3 the carry. I am not interested in intermediate carries. Intermediate carry of C0, C1, C2 I am not interested, but I need them for proceeding with my final computation. In order to complete my addition process I need C0, C1, C2, C3, C0, C1, C2, but what I am interested in is to find out S0, S1, S2, S3 and C3, that is my final result. So if I can now speed up the mechanism of generation of C0, C1, C2 and feed into the appropriate stages of the adder, full adder, I can get the result faster than that. Instead of having to wait for this carry to propagate from one to next to next to next to next like that, I can get it faster than that. So now how are we going to do that? We have already written for any given stage the C is given as, C output is given as. So I will write this as a generalized term, output carry I will call it Ci is Gi Pi Ci minus 1. That means the input carry is called I minus 1, the previous ith stage. For the ith stage output carry is Ci, C subscript I, Gi is Ai and Bi for that stage, Pi is A exclusive or Ai exclusive or Bi for that stage, Ci minus 1 is the carry coming from the previous stage. Now I can substitute for each stage now. For the first stage C0 would be, C0 will be G0 plus P0 C minus 1. Minus 1 I am putting, usually it is the first 4 bit, C minus 1 is 0, there is no input carry. But as I said as in the last lecture, it could be a stage in between a multi-stage 4 bits. I can have several 4 bits, this can be one of those intermediate 4 bit stage. So I cannot assume C minus 1 to be 0 all the time, so I am putting C minus 1. Or you want to call this C in if you are not comfortable with the word. C minus 1, put it C in, that is the matter. But this C in should not be confused, so that is fine. And C1 is G1 plus P1 C0. This is where the looking ahead comes now. C0, we have G1 P1, no problem. We are assuming that A's and B's are all available at once, the beginning of the problem. As soon as the addition is, as soon as you are asked to add, you are given the values of A0, A1, A2, A3, B0, B1, B2, B3. So I can always compute G0, G0, G1, G2, G3, P0, P1, P2, P3, all in one particular stage. Propagation delay will be there, but it is very small. But what is not there is the value of C0, which I have to get from this. So now I can substitute for this C0 in this equation. Can I not do that? It now become G1 P1. What is C0? It is G0 plus P0 P1 C minus 1. So I am substituting for the value of C0 from this equation. So now again I know G1, I know P1, I know G0, I know P1, P0, I have. So this stage does not require any extra time to wait for my carry generation. The carry generation is based on the propagation delay of this stage, which is not very much. It's a logic, two stage logic, is it not? This is a sum of products, so two stage logic. So there is a fixed amount of time delay, propagation delay, we have to accept that, but we do not have to wait for some propagation, some carry to propagate from one stage to the next stage. Continue on this, C2 will be G2, P2 C2, P2 C1, and if you substitute for C1 from here, this will be G2 plus P2 G1 P1 G0 P1 P0 C minus 1, and if you expand it, it will become G2 P2 G1 P2 P1 G0 P2 P1 P0 C minus 1. Again I do not depend on any value of C except C minus 1. Again it is a two stage logic, AND gates followed by OR gate. One set of AND gates feeding into an OR gate and then you get the output, and C minus 1 is already known. So no question of waiting for the carry to come through, and then you can write by induction. C3 would be G3 as P3 P2 P2 or P3 G2 P3 P2 G1 P3 P2 P1 P0 P3 P2 P1 G1 G0 P3 P2 P1 P0 C minus 1. So I have the equations for carry for stage 1, which has to feed into carry of this, which has to feed into this. I have the equation for carry of this, which has to feed into this. A equation for carry of this, which has to feed into this. So I have the carry equations of all. I have the carry equations for all the stages. I have the inputs for all the stages. All it needs to do is to find out the propagation delay of the individual full adder, which is of course that. I am not saying it is 0 propagation delay. I did not say that. The propagation delay is minimized. This can be appreciated when we are talking of multi-bit adder, in the sense of multi-bit adder, really 4-bit adder. What is 4-bit? Maximum 16 numbers, 0 to 15. But in computers, when you are talking of number crunching applications, we talk of 16 bits, 32 bits, 64 bits, 128 bits. Imagine the number of bits it has to, number of stages it has to travel in order to traverse to get to the output. There you can appreciate the speeding up here. Now what is this logic? All these G's and P's are known, because G is nothing but an AND combination, P is nothing but an exclusive OR combination. So I can have my P's and G's generated like this. AI, BI gives me PI. I have 4 such gates for P0, P1, P2, P3. I have G's, AI, BI, GI, 4 such gates, AND gates, A and BI. Then I have this logic in which I am going to feed my P0, G0, P1, G1, P2, G2, P3, G3. These have all been generated by that logic. 4 sets of exclusive OR gates and AND gates are fed into this. I am not showing it as a big drawing because it looks complex and then you lose the connections, you lose track of connections. And all I have to do is to feed in my C minus 1, which is a 0 most of the time, it is the first 4 bits. And what do I get at the output? I get C0, C1, C2, C3, correct? And what is inside this? Inside this is the logic for all these, each one of these. So there will be a gate structure to calculate this because the G and P are fed in and C minus 1 is fed in. This is an AND OR combination. There are going to be lots of AND OR combinations inside. I am not showing in detail. Number of gates will be more. For example, this will require only 2 gates, 1 AND gates for P0 and C minus 1 and 1 OR gate for these 2. This will require 3 gates, 1 AND gate for this, 1 AND gate for this and 1 OR gate. And this AND gate will have 2 inputs, this AND gate will be 3 inputs. The most complex gate, most complex circuit will be this, which will have 1, 2, 3, 4 AND gates. This AND gate will have 2 inputs, this AND gate will have 3 inputs, this will have 4 inputs, this will have 5 inputs, followed by an OR gate. So all these gates are only 2 levels, that is what I am trying to tell you here, the levels of transmission. The signal is given, A's and B's are given one level to get PI, that PI another one level, the PI and GI are calculated simultaneously. So after one level of computation or switching, PI gets computed, GI gets computed. So that is fed here. After 2 levels I get C's. So 1 plus 2, 3 levels, whereas if I have a multi-bit thing, it is going to take several, where each one of those things are 2 levels, going to 2 levels, so multiplication effect, it goes all the way. So I am buying speed at the cost of gates, I am paying for my speed in terms of gates, I pay gates, get speed. This is always the case, trade off is always like that. More expensive things, more good performance things are always more expensive, whatever it is. It is a general rule, of course, there are always exceptions. Sometimes the money cannot buy certain things, it has to wait for this previous process to be completed. Just because you have an extra person, if you have 2 persons, can I now say that if the 2 persons can do a job in half the time, but if the first person has to finish and hand over the job to the second person, 2 persons cannot do it faster than 1 person. There are exceptions like that, we are not talking those exceptions here. In general, conceptually, we pay by money, which in terms of gates or performance, in terms of performance is measured in terms of speed, cost is measured in terms of number of gates, but number of gates not only the cost, it also takes more power and more space and all that type of thing. Anyway, so 1 level, 2 level, 3 level I have C0, C1, C2, C3 and I need sum. What is sum? Sum is nothing but what? What is the sum of the full adder if you remember? S is A exclusive or B exclusive or C. So since I have A exclusive or B already and all these C's, one more level I get sum. So P0 exclusive or this is C minus 1, first stage of course does not need this C0 is the input to the second stage, this is the carry input to the second stage, carry input to the third stage, carry input to the fourth stage, carry input to the output. So this C minus 1 is not required, so if you want that C minus 1, this is Pi P0 exclusive OR, this gives you my S0. Sometimes the C minus 1 may be 0, as I said, it is the first stage, it is the first bit of a multi-bit addition. input carry is 0, so you do not need this gate, but I am putting it as a general scheme in which these 4 bits can be a slice of 4 intermediate bits of a much longer width. Suppose I have a 64 bit word in which I decide to do 4 bits at a time, and this can be an intermediate 4 bits wherein the previous carry stage will have to feed into this. So, this is a generalized drawing, even though in this particular case for 4 bit addition the A0 is the first bit and B0 is the first bit, this is not required. Sum is directly P0. So, not sum is directly P0. A exclusive or B, it's half adder. Now half adder is A exclusive or B was the full. We saw that in the last lecture, half adder sum, full adder sum. Half adder sum is A exclusive or B, which is P0. Now P1 is nothing but C0 with P1, S1, C1 with P2 gives me what? Yes? S2, correct. Why don't you say that? This one will give me S3 and this is C3. So, my final output is S0, S1, S2, S3, C3. If C minus 1 is there, this exclusive OR will be there. C minus 1 is not there, this will be S0. So, now I have one more stage. Now, the carry is generated. So, one gate to transmit, one gate to compute sum, one gate to compute these P's and G's, 2 levels of gates to compute carry. Now, this does not depend on the number of inputs now. So, the propagation is always same, it goes. So, in a multi-bit adder, the chain you can, each of these carry will be generated after 2 stages, that will be fed into the next stage, 2 stages. Every bit addition requires 2 stages of computation, and the last C0 will come, C3 will come. So, we are talking of 8 bits or 16 bits or 32 bits, even 4 bits, it is 8 stages. In this case it is 1, 2, 3, 4. Of course, some I have not taken into account there also. So, it is 1, 2, 3, carry is available after the 3rd stage itself. There the carry will be available after 8 stages, and some of course will be parallelly available. So, here also, but here some will be available after 1 extra stage. So, some will be available after 4 levels of gating, which is again faster by 4. So, this is as I said, I wanted to introduce a concept here. Cary liquid adder is one of the more basic techniques to improve the speed of addition, and arithmetics is not only addition. There are lots of arithmetic operations you have to do. You have to do subtraction, you have to do multiplication, you have to do division, and large numbers you have to make floating, you have to make exponential numbers whose magnitude is very large. You will have a radix and exponent, that type of representation. So, we have to take care of all of that, but the essence is all the same. Do we speed up? When do you need to speed up? What are the techniques used? There are several techniques, but one of them is this. It is one of the simplest technique to understand. But by this technique I want to drill home the point, I will bring home the point that it is always possible to have extra logic in order to accomplish certain things and make it faster. Now, of course, you can always argue that I am going to have large number of gates. Of course, I said large number of gates are required. I did not say it is free. You do not get anything free. If you can get this with the same number of gates as a full adder, 4-bit full adder, if you can get faster, who will think of that other one? It is a question of cost versus performance trade-off for performance versus cost. So, the cost comes in terms of these extra gates for that is why I put this as a separate black box. This is extra logic you need to provide. It is called CLA logic, Cary liquid logic. One other thing, the full adder concept is a very modular concept. without Cary liquid adder, if you remember, the full adder was right, and we had or you can even have this exclusive OR, A exclusive OR B, and what is that? Cary. Cary is A exclusive OR B, O, A and B, no? A exclusive OR B, C, and C, A and B. This is my Cary output. A full adder without Cary liquid head, we saw that sum is A exclusive or B exclusive or C. Cary we saw was can be written in two ways. Cary can be written as AB plus ACI plus BCI or AB plus CI into A exclusive or B. So I am using that option, CI times A exclusive or B, CI and A exclusive or B, or A and B. So now any number of stages, even though the propagation has to go from here, the C0 2 levels and then you have 2 levels, it goes on. One thing which is elegant here is the modularity of the circuit. That means whatever is the number of stages, all you have to do is to build an identical block. 2 bits, this repeated twice, 4 bits repeated 4 times, 8 bits repeated 8 times, 16 bits repeated 16 times. So sometimes it is easy to design circuits, especially when you want to build it. You want to build it in a given space. We talked about space being a premium in integrated circuit design. We talked about it in the beginning. The parameters are again to repeat the speed, the size, the cost, and the power dissipation, right. So the speed, you can pack nicely this identical circuits called modularity, modular circuits. Whereas here this will be all irregular. This AND gates will have 5 inputs, this will have 4 inputs, this will have 3 inputs, this will have 2 inputs, 1 input. So irregular structure of AND OR combination. At least if all the four Cary circuits, are they similar? No. This has 4 terms, this has 5 terms, this has 4 terms, this has 3 terms, this has 2 terms, like that it goes on. So there is a total irregularities you pay in terms of that. So the optimization of the design in terms of space and everything, that may in turn introduce some extra delay in wiring and all that type of thing. And another big factor is I put 4 gates, 4 stages, A0, B0, A0, A1, A2, A3, B0, B1, B2, B3. Supposing I had 8 bits, A0 to A7, B0 to B7. This equation will have how many terms? This will be, the last will be C0, C1, C2, C3, C4, C5, 6, C6, C7. The last Cary of the 7th bay, that is the bit 7, actually 8th stage, we call it bit 7 because we started with 0, 0 to 7. So the 8th stage, which is the 7th bit, bit 7, C7 would be, we will start with G7. This will be 4 plus 1 terms here, so that will be 7 plus 1 terms, 8 terms. That will have 8 terms and 1, 2, 3, 4, 5, 4 plus 1, 5, 9 terms. Not only that, how many inputs do this get? 1, 2, 3, 4, 5, that will have 9 inputs. So 9 input AND gate, 8 input AND gate, 7 input AND gate, 6 input, 5 input, 4 input, 3 input, 2 input, and all of them feeding into an OR gate with so many 9 inputs. So that will be a circuit which is sort of very unwieldy, and we have not really discussed that. Again, that aspect I have not discussed, some of those hardware aspects I have not discussed. Is there any limit on the number of inputs that a gate can have? We usually have 2 inputs or 3 inputs or 4 inputs. Is there any limit? Can I have 17 input gates? Can I have 47 input gates? Naturally the question arises. There are some restrictions on that based on the current levels, voltage levels, and the transistors can come in series, switching elements which are inside these gates which we have not touched upon. We are teaching this course at the system level, not necessarily system level, logic level. If you remember in the introductory lecture I talked about logic level, circuit level, subsystem level, system level, like that. So we are talking about logic level. When you break the logic, you see actual elements which form the circuit like diodes and transistors and resistors and capacitors. So when they are coming in series, there is going to be some problem. How many can you really put in series without suffering from the loss of the signal, without getting your signal, without your signal getting completely dropped to less than realizable, less than recognizable values. So these are issues. So there is a limit on the number of inputs. This is called fan in. The number of inputs that you can have in a gate is called a fan in. Number of outputs you can have from a gate is called a fan out. Fan in and fan out. Fan out is the number of outputs you can take from a gate to feed similar gates without degradation in the performance of the output, so that it can still maintain the 0 level and 1 level as per specifications. You have a 0 level specification in terms of currents and voltage, 1 level specification in terms of current and voltage for any gate. Suppose I say gate is 0 volts and 5 volts, it cannot be absolute 5 volts, it can be, there will be a variation, and it also tells you how much current it will deliver. If you go on connecting many outputs to this gate, a point will be reached when I will not be able to maintain the level that is required for driving the next gate. That is called fan out. The maximum number of gates you can connect of similar gates, maximum number of similar gates you can connect with the output of a gate, so that the levels are reliably maintained both in currents and voltage. Likewise, how many inputs can I give to a gate without any degradation in performance, so that the levels are reliable? This is called fan in. So there is a limit on this fan in and fan out for different families, different technologies. So I cannot go on arbitrarily adding the number of bits. I cannot say I will design a 27-bit Cary look ahead circuit. I cannot do that. Somewhere it is going to fail. So based on these conditions, so these are the two negative points of this Cary look ahead adder. The Cary look ahead adder positive is speed up and all that. We don't have to wait for the Cary to propagate. We are looking ahead and sort of, I won't call it prediction, it is not prediction, it is pre-computation. Prediction is something which can go wrong, it is a pre-computation. You look ahead of what is going to happen. The negative points are the non-uniform circuit. Of course extra logic is one negative point, that is we are willing to pay that, otherwise we will not go into this. Knowingly you go for, I will pay more money, give me a faster speed, faster gate, you are going to ask. I will give you more money, give me a faster adder. You ask for it, you got it. So that is not a disadvantage, I won't list it as a disadvantage. It is a technique of reducing the speed. But from a disadvantage point of view, there are two disadvantages. One is the non-uniformity, non-modularity of the Cary look ahead adder. Second thing is there is a limit on number of bits you can do for Cary look ahead. People say 4 is okay, sometimes 8. See, problem is maybe between 4 and 8, somewhere like 6 or 7 may be optimum, or 5 or 6 may be optimum. But unfortunately in digital we always do with 0, 2 powers always, for some convenience and sometimes for practical reasons. We do 0, 1, 2, 4, 8, 16 like that. It is very rare to find a 7-bit adder in the market. You can buy an 8-bit adder, you can not buy a 6-bit register, you can buy a 8-bit register. Of course you can always build one, but that is not what I mean. So 4 bits, sometimes 8 bits are done. So what happens if I want to do really a multi-bit addition like 16 bits or 32 bits or 64 bits? There are two options. I can go in for, I can divide this into 4-bit, 4-bit, 4-bit in a Cary propagation mode, and within each of those 4 bits I can do a carry look ahead. So first bit carry look ahead, first 4 bits carry look ahead, output carry will trigger the second stage, which is again. So instead of having 64 times the propagation delay, I will have only 16 times the propagation delay plus the extra propagation delay for each carry look ahead stage. That is one option. The second option is within that I can do a carry look ahead. I can do a carry look ahead of the 4th stage, 8th stage, 4th bit, 8th bit, 12th bit, 16th bit, and use another carry look ahead logic to generate higher level carry look ahead. So I can go on doing it, cascading in levels of carry look ahead also can be done in different levels. I can have a 2 level carry look ahead, I can have a 3 level carry look ahead, I can have a 4 level carry look ahead. So carry look ahead along with transmission serial carry propagation combined with carry look ahead is first option, where I will have 4 bit carry look aheads connected in carry propagation mode. So the speed is reduced somewhat, speed is increased somewhat, propagation delay is reduced somewhat. The other one is if you want to do even better than that, within the carry look ahead output, so I look ahead the carry for the first 4 bits, at the same time I can get carry for all of them. I can look ahead for carry for the 8th stage, first 4 bits I can do, second 4 bits I can do, third 4 bits I can do, all of them can feed into another carry look ahead stage. If it is not sufficient I can go to one more stage like that. That is more and more complex circuit, that means more logic, when you have more logic and more non-modularity. So again there is a trade off, there is a speed variation. I can have a menu now, no carry look ahead for me, give me, I will do a modular design with full adders, I am happy, the speed is good enough, take it. Okay, I want an improvement in speed, so I will do carry look ahead, but I do not do more than 4 bits. Give me any number of bits, I will divide it into 4 bit, 4 bit, 4 bit, and each inside I will do carry look ahead, but outside I will connect as carry propagate. That is second option. So more logic, increase speed, so you pay for it, but you know that you pay for it, and the modularity and that all that extra fan considerations you have already taken into account. Third is I am not satisfied with the speed you are going to get with this, I want much faster, then I can this carry look aheads can the output carry look aheads, the carries of the 4 stages, 4 stage carry look ahead can be used in a second level carry look ahead to get a carry generation much faster than the other one. So this requires 2 level carry look ahead design, which is going to be slightly more complex in terms of hardware, in design complexity, number of gates, and thereby the non-modularity, size, etc., all those problems come again here also. But let us not go into all that, we will talk about at most carry look ahead connected in propagation mode. Suppose you want to build a 16 bit carry look ahead, 16 bit full adder, I will probably do it at 4 carry look ahead adders, C3 feeding into second stage, C7 feeding into third stage, C11 feeding into the fourth stage. That is good enough for this class. But I wanted to introduce, so basically even though carry look ahead as I said is the example I use for speeding up, this is something which you should be sort of familiar with as a conceptual level. Arithmetic circuit I have lots of, that is a design, that is the beauty of design versus analysis. Analysis, there is an analysis, you have to lead the analysis, that is all, somebody else does the analysis and you just understand and learn it. A design you have options. What are the various techniques by which you can speed up based on the consideration, based on the design requirement, based on the cost, based on the performance requirement you decide. That is where the design concept comes in. So I just thought I will introduce this concept to you. This is a general concept in terms of hardware, extra hardware can reduce the propagation delay or increase the speed, or extra hardware can improve the performance in most cases. That qualifying class I want to always put, because there are some cases where extra money cannot buy what you want. So this is not always possible. Okay.